All we did was third law. We did
That was Newton's third law, was just identifying Newton's force pairs. What we're going to do now is do a few examples of Newton's second law. Okay? So let's consider this a book on the ground that's being pushed along the ground, okay? Let's see what would happen. So I'm gonna say that this is 1 kilogram. Let's say that there's a force that's exerted on it off to the side of, let's say it's 5 newtons. Remember, Newton is a kilogram meters per second squared. That's the unit of force. Okay? And this force is being exerted by some outside agency, me pushing the book. What is acceleration of the book? Well, this is an application of Newton's second law. And so what we would do is we would just add up the forces on here. So if I were to draw a free body diagram for that book, what are the forces on it?
Gravity.
I have a weight on the book. I'm just going to call it W.
The table. Of the ground.
You have a normal force pushing it upwards.
And then you have your force.
We're going to have this applied force.
Mm-hmm.
I'm just going to call that F, like there, that 5 Newton force. Okay?
Is friction something where...
Let's not worry about friction for now. Frictionless table. Friction will really complicate things. For a little bit. We'll deal with that in a little bit. Okay. Well, is this thing moving through the table?
No.
Okay. Let's go ahead and write all these vectors in components. Introduce a coordinate system, write all the vectors in components, add them up, because we have to do that, and then set force total equals to MA. So force total equals MA. That's our starting point. This will be a starting point for for a ton of problems. Most of the problems we do. The total force will be Newton, or normal force, sorry, plus the applied force, plus the weight.
So is N the 5N or is F the 5?
F is a 5N,
Okay, just making sure.
which would be mass times the acceleration. Okay. All right, so we have all this. Let's go ahead and how do we add up forces? Remember, we have to split them up into components, right? We have to introduce a coordinate system, split them up into components. So let's introduce a coordinate system. I'm going to do y upwards, x like that. And then we can look at x and y components of this equation. So n would be the magnitude of n, y hat, right? Because it's all in the y direction. What's the weight? Would be the magnitude of the weight. We haven't talked about what that is yet. And it's in the negative y direction, like so. You see that?
Mhm.
And then the applied force, what direction is that in?
X.
X, and we know how big it is. It's 5 newtons, right?
Yeah.
So I would have 5 newtons X hat, like so. Is that good?
Would that be absolute on it?
No, it's just a number. Yeah, the absolute, that just means the magnitude of the vector.
Oh, the
That's all.
magnitude,
So if
okay.
we knew it, the normal force was 100 newtons, I'd just write 100 newtons there.
Okay.
Okay? Like good. All right, so let's go ahead and add up those forces and set it equal to MA. So forces in the y direction. Let's look at the sum of the forces in the y direction. I have the normal force in the y direction, right?
Mhm.
The weight points in the negative y direction. And that would equal the m times the a component, or times the y component of the acceleration. Make sense? Sum of forces in the x direction would be equal to what?
The F, the 5N.
5 newtons, which is m times the mass times the acceleration in the x direction. If that book is sitting on the table, is it accelerating or even moving at all in the y direction? This is a key point. If it's sitting on the table, no acceleration in the y direction. So this would be 0. And so that would mean that a sub y is 0. Also, this would tell you that the normal force is magnitude of the normal force will be equal to the magnitude of the weight force. See, I have normal minus weight equals 0 now. That means the normal force is equal to the magnitude of the weight force. Okay? So, but we're not interested in this for this problem. The problem we're interested in is what's the acceleration? Y direction is 0. This is our other equation that we get from Newton's second law. We know what the mass is, right?
So we divide it by
So we get 5 newtons is equal to 1 kilogram times a sub x. And divide both sides by 1 kilogram. And I would get that a sub x is 5 newtons per kilogram. So that's a meter per second squared. So if I were to write out the a vector, 5 per second squared x hat. Like that. Okay? You guys follow that?
So that would be because of X, it's going in the X direction.
Yeah, there's only acceleration in the x direction if I'm pushing it like that. There's no, since it's sitting on a table, there's clearly no acceleration in the y direction. And that's because the normal force balances the weight force. Yeah.
So
Okay.
like, if every time we see a problem that if there's no acceleration in the y direction, can we just go directly to that formula and plug in numbers and get the answer instead of doing all that?
Well, so that works if there's only one mass,
Yeah.
but if I had other masses stacked on top of it, and we're pushing it like this, I have to be a little bit careful, say, if I want to get the, the,
You're applying your force to your foot. You're not actually applying the force. Sorry,
force sideways to it, and that's the friction. We haven't, yeah, we'll get to that. Well, the masses are given. So, let's do another example with one mass, okay, just a little bit. Okay, let's say I have a box on the ground, but this time the box has a rope on it attached to it. And it's pulling it up at some angle. So this is a rope. Somebody's pulling on the rope with a tension force, or with a magnitude of a tension force of 100 newtons. And let's say that this box has a mass of 20 kilograms. Let's say the angle here is 30 degrees. So here's questions. One, use Newton's second law to find acceleration of box. And two, this is something that's going to introduce something new about what the weight force actually is. What is the normal force between the box and ground? Two questions. And then no friction. We'll add friction later. All right. So before I do this problem, there's one thing I want to introduce. If I'm on the surface of the Earth, I have a massive object, and this is near the surface of the Earth, I would say. And by near, I mean, probably within 50 kilometers or 100 kilometers of the surface of the Earth. So anything in daily life. If I have a mass here, and if I were to draw a free body diagram on this mass, I have a weight going downwards, normal force going up. This weight, the magnitude of that weight is m times g. Okay? Where that's the mass times that g, which is the 9.8 meters per second squared. So magnitude of the weight force, the gravity force, is m mass times g. So for instance, for here, the magnitude of the weight force would be 20 kilograms times 9.8 meters per second squared, which would be 196 newtons. Yeah.
Where did you get the 9.8 meters per second?
So that's the magnitude of the weight force. It's mg.
Oh, that was given?
Well, this is something I'm introducing. Near the surface of the Earth, the magnitude of the weight force is
Oh, I follow you. Yeah, that's like
Okay.
the accepted value.
Yeah, this is what the weight force is
Yeah.
near the surface of the Earth. It's MG. It has units of mass times acceleration, which is the same units as force. If we know that this is the case, because if you didn't have any other forces on it, just had this thing accelerating downwards. I know it accelerates with, and so this would mean that the total force, weight, would be M, V, and it's in the Y direction. This is MA, this is A. If all I have is gravitational acceleration. And so this would be the magnitude of the weight force. Okay, let's see if we can get this one. I mean, I think we can get part A pretty quickly. Okay, let's draw a free body diagram. So free body diagram. Start out with that. On the mass. Don't worry, I'm gonna call about sick kids. So I have 100 newtons going that way, the tension force. I'm just going to label it with that 100 newtons to start out. Maybe I should just write tension force here. I'll just write tension force. We'll label it like that to start out. What other forces do I have on that block?
Gravity.
We have the weight of the block going downwards. Anything else?
The normal force.
The normal force from the surface it's on. All right, so let's write out all these forces in components. So I'm going to draw y, x like this, okay? What's the weight force in components? So how much of it points in the x direction, how much of it points in the y direction? So it's negative mg y, right? This is how much it points in the y, negative y hat direction. So in this case, that would be negative 196 newtons in the y hat direction.
And that's your weight times gravity.
This is just mass times gravity. Yeah. Times that. You follow this? You got it? Okay. Normal force. Well, right now, all that we know is that it points in the y direction. We don't know the magnitude of it. How about the tension force? How much of the tension force points in the y direction and how much points in the x direction? Yeah, that's what you have to do. Let me write my... So if I were to draw this tension, this length here would be the amount of tension in the x direction. This here, tension in the y direction. This magnitude of tension is 100 newtons, and this is 30 degrees. So how do we get how much of it points in the x direction?
So it would be adjacent over an opposite.
Yeah, so cosine of 30 degrees would be Tx over the magnitude of the tension.
Yeah.
So that means that the amount of the tension in the x direction is magnitude of the tension cosine of 30 degrees. So this would be square root of 3 over 2. Oops. I'll tell you what, I'll just write it in terms of cosine. 100 newtons cosine of 30 degrees x hat. How much of it points in the y direction?
187
Yeah.
Plus 100 newtons sine of 30 degrees y hat. You guys follow? All right. Cosine of 30 is square root of 3 over 2, which is like 0.86 something. Sine of 30 is 1/2. So I could write that as 86, I think, is it 80? What is, somebody do this real quick and tell me what it is for round. 86.6? Okay, so it would round to 87 newtons if I took it just to full numbers. Plus 50 newtons, and this would be x hat plus y hat. And I'd have to leave it like that. All right. So let's sum up the forces in the x direction. Set that equal to m acceleration in the x direction. So what are the forces in the x direction? If I add up all those forces. This means sum, by the way. The sum of the forces in the x direction.
87.
And that's it. There's no other.
That's it.
There's no other, right?
No.
That means 87 newtons is equal to ma sub x, which is 20 kilograms times the acceleration in the x direction. So what would be the acceleration in the x direction?
4.33 meters per second.
Yeah, divide both sides by that 20 kilograms.
Mhm.
So what was that again, Samantha?
4.33 meters per second squared.
4.33 meters per second squared is equal to the acceleration in the x direction. If this box were sitting on the ground and is it accelerating in the y direction? No, it's just, no, you can test it to see. Here's one of the interesting things. This normal force will be whatever it has to be to keep it from accelerating in the y direction up to a certain maximum value. And that maximum value is the weight. So I have 50 newtons in the positive y direction, normal force in the positive y direction, and negative 196 newtons downward. 196 newtons downward. So this normal force plus this will be equal to that, so it doesn't accelerate in the y direction. And the normal force will be whatever it has to be for that to happen. So acceleration in the y direction is 0.
So the force in the y direction exceeds the
Normal.
weight. Yeah.
Exceeds the weight. If it exceeded the weight, then I'd be pulling it upwards, yeah. Okay. And there wouldn't be any normal force because it would be off the table. Okay? All right, well, I'll let you guys go. Probably. We'll talk about